Well, good morning. This will be our first class on rocket propulsion, and in this class today what we will look at is what is the subject on rocket propulsion, how it differs with different propulsion subjects, what are the aspects we must consider. We will go through the course contents what we have and then see the type of books what we must be referring to, and then get started with the course. Maybe the introductory part will take something like 10-15 minutes, and then we will get started with the course. Having said that, let's first take a look on what this subject on rocket propulsion is about. The word propulsion, if you see, comes from the Greek word, it's known as propellery. Propellery. The word propellery in Greek means push, therefore we are talking of something pushing. Pro, as you know, means something like forward or before. Therefore the word propulsion means push forward, and therefore whenever we talk of any subject on propulsion, what we mean is pushing forward. Let us take the simple example of, let us say I have something like a car which has to climb up a hill, up an inclined plane. What we do, the engine of the car pushes it forward, and by pushing I mean you are changing the velocity of the car, or you are imparting a momentum to the car. What is momentum? Momentum is change of what? You are imparting some change of momentum to the car. How would you define momentum? How would you define momentum? What is momentum? How will you define it? Anything? We say the car has a velocity v, it has a mass m, you say mass into velocity is what is momentum, and if you want to change the momentum, you change the velocity of the car, you give some velocity and you have what we call as momentum. Is it right? Now in space, deep space, we do not have something like atmosphere, and therefore the act of imparting momentum to the object in space is what we deal with rocket propulsion. I will again repeat this. All what we are saying is propulsion means pushing objects, and when we say rocket propulsion, we are dealing with pushing objects in space. Space means anything beyond us, maybe up there. Therefore maybe first we must get an idea on what space is about. Let us say what we mean by space we have to understand, but before getting that, let us just quickly get through some idea on what this whole course is about and how we are going to organize our next, let us say 40 classes or so. To be able to organize ourselves, let me get started here. Maybe the first class starting today, we will look at what we mean by the word space, what constitutes space, in what way is motion in space going to be different than motion on the ground. That means we talk about motion in space, and once we know how motion takes place in space, maybe we will be able to find out what is the exact requirements that a rocket must do. See, to be able to say I design a rocket could be something very small or it could be huge. I must know what is the requirement of motion in space so as to go and make a particular rocket. Therefore the first chapter will deal with motion in space and how we go about converting this motion in space to the requirement of a rocket. Once the requirement of a rocket is clear to us, the second chapter will deal with, let us say, the theory of rockets, I would like to ask a question, why should a theory of rockets be different from a theory of a car? Or let us say I have a gun, I fire a gun, the bullet leaves the gun. In what way is a rocket different from a gun? What is your thinking on it? Anybody could answer that? Pardon? You say it's a non-air breathing system. So what? We will get into some details of air breathing, non-air breathing. Your point is it's a non-air breathing system, but in what way should a rocket be different? Let us say I have a gun, I fire a bullet from a gun, I am also leaving it at high velocity. Why should we call theory of rockets? What is the great theory about it? See, it so happens, what happens is in a particular rocket, let us say, we just assume a rocket is like this. There is some mass which is available in the rocket. What is the mass which is available in a rocket? The mass must be able to push forward. That means it propels the object. And what is the object? You have something like a space capsule which it pushes forward, and this what propels is what we call as a propellant. By propellant in a rocket you mean the substance used for pushing up the rocket or propelling the rocket. Now in the case of a rocket, the propellant is continually getting exhausted, it leaves the rocket, and therefore the weight of the rocket keeps coming down, and therefore compared to a car in which I carry something like 10 liters of petrol or something like this, I carry tons and tons of propellant which is ejected out, and therefore the theory of a rocket is different from a car or a bullet, and therefore we have to look at the theory of rockets, which is the second chapter. Having finished the second chapter, we will have to say, we told ourselves to push an object we need to give change of momentum, and therefore we will go into nozzles which produce high velocity and help us to achieve a large change or impart a large change of momentum to the object in space. You all have studied nozzles in your gas dynamic course, right? Now anyone has not done it? Or we will start from the basics, go through the basics of nozzles, advanced nozzles, but it is quite an involved chapter, because if you have something like a rocket, again let me sketch another rocket for you, maybe the internal configuration. I have something like a nozzle here. The flow must run full, otherwise if some portion does not run full, I could get something like a side force in addition to getting a force in this direction. Therefore the theory of nozzles is quite involved, and the third chapter we do here is on nozzles. The fourth chapter we will get back into the propellants, or what is used for propelling could either be a solid propellant, could be a liquid propellant, could be a gaseous propellant, could be a hybrid, a combination of these things, could be electricity itself, could be nuclear, could be anything, right? And therefore in the fourth chapter we will study about the different propellants, what are the characteristics required to make a good rocket, and that is what we will study about the propellants: solid, liquid, gas, hybrid, electric, maybe nuclear propellants. Once we are clear about the propellants, we can go into the details of the rockets, and then we will ask ourselves, well, the fifth chapter would be solid propellant rockets, and this type of rockets has been used very extensively in India, both for GSLV, PSLV. Maybe we will have to look at it, look at the design considerations, what constitutes a solid propellant rocket. The sixth chapter would be something on liquid propellant rockets. They are more versatile, and in this chapter we will basically look at the following. Maybe we will take a look at what are the cycles of operation. in what way it differs from a gas turbine combustor, maybe an IC engine, and what are the modeling features. You know, the liquid propellant rocket is something which is evolving, and when we talk of cryogenic propellants, it is again a form of liquid propellant, and therefore we will spend quite some time on this. The 7th chapter would be something like, maybe since we have studied solid and liquid, we can study something on hybrid and something like a single propellant, what we call as monopropellant rockets. This would finish the different types of rockets, how to make them, what are their features, and what are the problem areas in rockets. And once we are clear about it, we go to an advanced subject which I will call as combustion instability. See, this particular chapter on unstable combustion and instability is particularly important for PG and research students, since we are going to look at what causes, instead of having a steady thrust, will it oscillate under some conditions, instead of burning steadily will it explode under some conditions, and that is what we study on combustion instability. We will deal with it in something like 6 to 7 classes. It tends to be important, and this is some area wherein research work still goes on in the area of rockets. The 9th chapter will be an evolution of some of these things. Maybe we will look at electrical rockets. What do we mean by electrical rockets? We told ourselves for any rocket we need to push an object in space. We will try to see how we can generate electrical forces, different forms of generating electrical forces or forces using electricity or magnetic electromagnetism, and then we will deal with this particular chapter on electrical rockets. The 10th chapter would be on nuclear rockets, and other advanced rockets. What do we mean by nuclear? I could use nuclear energy to generate a force. I could also use, maybe I could use space time curvature like relativity to generate a force, and some of these things we will consider as the last segment of this course. Having said that, let me also briefly brief you on 1 or 2 books which I will be following, which are good books for this particular course. The first book is by Sutton. It is on rocket propulsion elements. I think the publisher is Willy. Year of publication is 2001. You know, this book gives a very good description of rockets, but the mathematics of rockets is missing, and I published one book. The name is Rocket Propulsion. It was published by Macmillan in 2010. This was based on my teaching of the course over the last 6 to 7 years. A third book which gives good description about the different rockets is by H.S. Mukunda. The name of the book is Understanding Propulsion. It is published by Interline, Bangalore. And I think it is in 2004 what was published. I think one important book which I should have put at the beginning is a book by Hill and Patterson. The name of the book is Thermodynamics of propulsion. The publisher is reading. It is an old book, it was first published I think in 1970 or so, but the second edition is published in 1992. We have copies of these books in our library, right. Therefore, this is a beautiful book, deals with the thermodynamics of propulsion. This deals with a description of many of the propulsion elements. This combines aerospace and rocket propulsion together, whereas this is little bit more mathematical in the area of propulsion. We should keep this, and as I go along maybe I will introduce more books on specific subjects. Well, this is the background of the whole course, and I think let us get started now. Let's get started. What do we mean by motion in space? Anybody would like to hazard a guess in what way it will be different than on ground? Let us first define what is space. How do we define space? Anything above is space, can we say, or how would we define space? We go on up and up, or we go sideways, go to infinity, that is space, or how can we define space? How do you define space? We talk of space capsules, we talk of some planets, we talk of galaxies. How would you define space? See, you are telling me that anything outside the atmosphere is space. Therefore, let's take a look at your question and examine what really space is about and what do you mean by atmosphere. Let us say we are here, let us say in Chennai over here. Chennai is normally hot, and let us try to plot the temperature in the air or in the atmosphere above Chennai as a function of, let us say, the altitude, say Z. You know, we say since the sun is heating the earth tends to get hot, maybe the temperature at the surface of the earth, let us say, is around 35 to 40 degrees centigrade. As we go higher and higher up, that means as we increase the altitude, the temperature decreases until at an altitude of around, let us say, around 10 to 11 kilometers, the temperature is around minus 50 degrees centigrade. These are notional numbers, and thereafter the temperature begins to increase again. That means temperature drops to minus 50 degrees centigrade at an altitude of around 10 kilometers and then begins to increase again. Why does the temperature decrease? The earth receives the radiation from the sun, gets heated, and the surface of the earth is relatively hotter, and as you proceed away from the surface the temperature drops, and this zone wherein the temperature drops is known as troposphere. The reason why temperature drops is earth is relatively hot, as we go higher up the temperature drops. A jet aircraft flies at an altitude of around between 8 to 10 kilometers. Let us say this is where the jet aircraft flies, and it flies where the ambient temperature is between minus 40 to minus 50. You would have heard this announcement saying your aircraft is cruising at an altitude of around 10 kilometers, wherein the ambient temperature is of the order of minus 45 degrees centigrade or minus 50 degrees centigrade. If you go up still further, the temperature increases. The increase in temperature is because in this area you have lot of ozone available. The ozone sort of gets heated by the solar radiation, it absorbs the solar radiation, the temperature increases, and this increase manifests for another 40 to 50 kilometers, let us say 50 kilometers, and the region of the increased temperature is what we call as the stratosphere. But when we go still higher altitude, let us say higher than 50 kilometers, the pressure in air is so small or the molecules of air are so small that they are unable to absorb any radiation, or because there is nothing here absolutely, therefore the temperature again drops to an altitude of let us say around 100 kilometers or so. But if you go to still higher altitudes, you have the molecular oxygen which absorbs, the molecules individually absorb the radiation and they increase in temperature, and you have the temperature going up. The region wherein the temperature drops again is what we call as the mesosphere, and the region of temperature increase because the individual atoms of let us say oxygen or let us say molecules of oxygen, they absorb the radiation, that is individual atoms getting heated or individual molecules getting heated is what we call as the ionosphere. This continues for something like 100 200 kilometers. If I were to plot the pressure of air, the pressure of air may be as a function of altitude, again I plot the pressure. This is altitude Z in let us say kilometers. At the surface of the earth the pressure is around 100 kilopascal, and the pressure monotonically drops, keeps on falling until maybe at the ionosphere you hardly have any traceable quantities of air left, it is all free molecular flow, and this is where we said that the temperature increases. The concept of temperature fails because there is no continuum in this region, and it is the individual molecules of some of these gases which tend to get heated to high temperature and the temperature increases again. Now the question is, what do we define as space? Anything above the surface of the earth going through the troposphere, stratosphere, mesosphere, ionospheres and beyond, that means we say space is sort of endless, it keeps on going to infinity, and therefore we must be capable of defining what constitutes space, which I do subsequently. There is no extent itself. But how do you define something which is endless? Therefore, it is necessary to have a look on what constitutes, what is there in space. And if you go back and see what is there in space, you see that there are something like 1.5 into 10 to the power 11 galaxies, not in total space, but in the space which we can see, which we can observe. Rather, I must correct myself and tell you that in the observable part of space, and how do we observe? Maybe through a telescope I observe something. In the observable space we have something like 1.5 into 10 to the power 11 galaxies. That means space is still beyond, but what I can see is only this. And what are galaxies then? See, all of a sudden we are introducing new words. By galaxies we mean you have typical stars, gravitationally bound system of stars, and each galaxy has a system of stars and lot of maybe some dark matter, something like gas, dust and all that. It could contain lot of things, and out of these 10 to the power 5, 1.5 into 10 to the power 11 galaxies, if I consider one galaxy to which we belong, that we say is the Milky Way galaxy. Right? Therefore, what we have said is space is endless. In the near observable space we have something like 10 to the power 11 galaxies, and our attention has now come to the galaxy in which we belong to or in which we live, which is called the Milky Way galaxy. Why the Milky Way? It comes from some Roman or Greek mythology which says that the color is something like milk and stuff like that, or there are some stories around it. We will not get into those details, but just say maybe when we talk of a number like 10 to the power 11, we are something like 1 over 10 to the power 11 part of observable space, and when I talk of a number like 10 to the power 11, even though I write it like this, it is as if saying that on the beach you have lot of sand particles, and I go and put all the beaches together and I take one sand particle, this is the amount of space I am considering from the near observable space. Therefore, we have shrunk ourselves, and you can see how small we are in relation to space really. And this Milky Way galaxy, if you really see what constitutes the Milky Way galaxy, well, in the Milky Way galaxy you have a large number of stars, and what are stars? Massive objects in which nuclear reactions are taking place. They emit light, they emit heat. Then you could also have something like dark matter. You could have in between the stars, you could have some gas and stellar dust, or dust as it were, let us say dust, you could have gas. You could also have lot of different things, you all would have heard of black holes. What are they? We could have it we have it in our Milky Way galaxy. What are black holes? What happens is sometimes these stars shrink to very small size. Therefore, you have infinite mass concentrated in a very small volume, and when you have large mass concentrated in a small volume, it is capable of attracting, that is the gravitational pull will be large. We will get into the gravitational pull towards the end of this class, and therefore what we say is we will have black holes. We could have other objects like quasars. What do we mean by quasar? Quasi thing related to stars, quasi star related radio sources, quasars, and these quasars are objects which are again travelling at near about the speed of light itself. Therefore, you have lot of things there in our Milky Way galaxy, and out of all this, out of all these stars, I figure out one star which I call as the Sun, and therefore we focus ourselves, maybe from 10 to the power 11 galaxies we have come to one galaxy. Out of all this we have come to the Sun, which is a single star, and it is about this which we will be basically interested in. Let us put it together. Let me put some dimensions out. If you look at the Milky Way galaxy, sorry, let us see the extent of this. It is somewhat cylindrical in shape. The size or the diameter is around 10,000 light years. Why do I say light year and not say kilometers? Because it is so huge, and what is a light year? The distance travelled by light in 1 year. The speed of light, as you know, is 10 to the power 3 into 10 to the power 8 meters per second. In 1 year I have 365 days multiplied by 24 hours multiplied by 60 per minute, 60 per second, and therefore 1 light year will therefore correspond to so many meters, which should be around, I think, something like 10 to the power 11 kilometers or so. Approximately it will come to around 9.5 into 10 to the power 10 kilometers or so. Therefore, we are talking of a diametral content, and it is something like cylindrical in shape, and the depth of this is something like 1/4 of this, something like 2500 light years. And in this you have number of stars, as we say, number of objects, and we are considering one particular star called the Sun, which we say is the solar system with which we are concerned with. Therefore, this is all in space, right? We started with number of galaxies in the endless space, and now we come to the solar system. What does the solar system consist of? It consists of the Sun, a single star, mind you, out of the large number of stars, and you have a number of planets, maybe starting from Mercury, then you have Venus, little bigger, then we have the Earth. What is next? Mars. What would be the next one? Venus, Then what further? Let us say I continue this over here. Mars, then Jupiter, okay, fine, yes, Mars, Jupiter, I am sorry. Then is Venus. No, then what will be the next one? Saturn. Two more. Neptune, Uranus and Neptune. Therefore, you have 3 plus 5, 8 planets which are going around. Previously we had another planet known as Pluto, but that has been decommissioned because it is not fully formed. It is something like a loose mass which is still going along with a belt here which is known as the Kuiper belt. I will come back to this belt because it gives lot of inputs, what we need to do, what we need to understand about maybe some asteroids coming and hitting the earth and all that. We will get back to this shortly, but all what we are saying is, in the solar system we have something like 8 planets going round the sun, and this is the near part of space with which we are interested in. This solar system also consists of something like 31 moons. And how do we define a moon? We tell ourselves, yes, there are certain objects which go round the planets and they go round like satellites around it. There are 31 moons, and Earth has a particular moon which is going round the Earth, and this is the moon of the Earth. So also we have moon for Saturn, we have moon for Jupiter, and there are something like 30 other moons which are available. When we are dealing with all this, it is necessary to have some idea of what constitutes these planets. Maybe Earth, if we take, let us put down the mass of the Earth, let us put down the diameter of the Earth. I have it with me here, let me 5.974 into 10 to the power 24 kg. The diameter of the Earth is 12,756 kilometers. I think these numbers are important. I will circulate a table to you giving the mass of the different planets and their diameters, but just to get an idea, maybe Mercury is about the smallest planet, around 1/3 the mass and diameter of the Earth as it were, while I think the largest would be something like Jupiter might be the largest planet what we have. Having said that, what happens, all these planets go round the sun, and it is this motion of planets which give or which prompted Newton to formulate the universal law for gravitation. I think I should repeat this point in a slightly different way. Let us take a look at what I want to say. Let us quickly revise through what we have done so far. We said propulsion or rocket propulsion deals with pushing in space. If you want to push in space, we need some force to push, and therefore the one of the forces which we should consider is the gravitational force. Let's start with that. To be able to understand the gravitational force, it becomes necessary for us to go back into the solar system, look at the revolution of the different planets around the sun as it were. Now let us just see, let us just take one particular case. I take the Earth here, and I say it is going round the sun, maybe let us say the sun is over here, Earth is going round the sun as it were. People have been watching the motion of planets around the sun for years together, and in maybe around the year 1600, maybe 1570 or so, 1570 to 1610, we had a famous person by name Johannes Kepler. he indexed 3 laws which govern the motion of planets like Earth around the Sun. His thing was, he said there are 3 laws, and what are the 3 laws? Let us quickly get through before, because it will help us to find out what we mean by the universal law for gravitation. He told the following: all planets move in elliptical path, have elliptical orbit. By orbit I mean the path of the planet around the Sun, as it were, and we are talking all the path will be elliptical. But if you read the newspapers, around a month back there was a news that the orbits are not really elliptical, but they are wavy orbits, something like this it is going on. Well, some work is still going on, we will not get into those details, but as per Johannes Kepler, we have the orbits in an elliptical path, one. Second is, he also had the second law which said something on equal areas. What is equal areas? He said, supposing we have a line in which we join the center of the Sun with the center of the Earth, and then we find out what is the area swept during the elliptical orbit, he finds that the equal areas are swept out in equal times. Let us just put it together. This is the Sun which is at the focus, and you have something like an elliptical path. Let us say this is the major axis, and then you have an elliptical path, this is the second foci, you have an ellipse as it were. This is the Earth going round the Sun. First law says it is an elliptical path. The second law says maybe equal areas are swept out at equal times. If this is the time taken for this area is swept out by the imaginary line joining the center of the Earth with the center of the Sun, and similarly in an equal area will be swept out during the motion from here to here. All it tells is, maybe if I come to this particular path in which I have minor axis, maybe it will travel a longer path here compared to a shorter path in this particular one. This is the second law for the orbit which is given by Johannes Kepler. The third is one which says about symmetry of orbits. All what it tells is, you have the Earth, you have maybe Mercury nearby, you have maybe Neptune far away. It tells that the time of one revolution divided by the radius is such that the orbital time t squared divided by the distance cube, that is the distance from the Sun to the different planets, divided by the time of orbit of the particular planet, is a particular constant. These are the 3 laws for orbital motion as formulated by Johannes Kepler. Why are we getting into orbital motion? We are just talking of space, we want something to understand something about gravitation, and therefore you have these 3 laws, and then comes Newton much later. And what does Newton find? See, the story goes like this. Maybe he is watching an apple fall on the ground from a tree, apple is falling. He immediately connects the apple falling from a tree to the elliptical orbits or orbital motion of the different planets around the Sun. What is the commonality? How can we, what is the common factor between these two? Let us take another look at it and come back to this question of what decides what is planetary motion, what we are dealing with it. Let us say this is the Sun as it were. Let us say that the Earth is going round the Sun like this. Maybe the Earth is going, when the Earth travels some distance like this, it falls through some distance because it is elliptical. Again the Earth, let us say if it had a horizontal velocity, it will go like this, but in the process of going horizontally it falls through some particular distance. Again it goes through some, it comes over here, again it comes like this. In other words, if I had given a horizontal velocity to the Earth, it keeps on falling towards the Sun at each instant of time. In other words, if the Earth were to go horizontally at a velocity, it falls by a certain distance as it travels. That means I have a constant velocity and it keeps falling, therefore it is as if the earth is freely falling. It is no different from an apple which falls onto the ground. Actually, if we look at ourselves today, all of us are just freely falling towards the sun, just in the same way as a fruit or a stone is falling from the sun. Therefore, he says, well, there must be some commonality between an apple falling to the ground and the planets falling towards the sun, and it becomes something known as the universal law. See, see, the point is, Newton did not do experiments by himself. He did nothing to really say that I derived the gravitational law like this. Just based on observations of Johannes Kepler, and of course you had one or two more people like Galileo Galilei, who as you know dropped a piece of a feather and an iron ball and found that in vacuum both of them will take the same time to come to the ground. Just based on these two small observations, he was able to formulate this law. But before I get into the gravitational law, it is necessary for me to go into some more details, like how do you measure, because when I say some force and all that, we must be a little more clear on what are the parameters we must use describe motion in space. I think we must be very clear, because a time has come when I would like to put some numbers, like to put some equations, I must know how to express myself. Therefore, immediately we say, hey, we are all engineers, yeah, we know about mass, length and time. I can use these three fundamental quantities and describe it. How will you describe mass? Quantity of matter, unit is, unit is kilogram, well said. But what is a kilogram? It is some reference kept in a lab near Paris since let us say 1819 or so. Some standard is kept, it is kept very carefully in a desiccator under very controlled conditions such that nothing will going to happen. It is a platinum rhodium alloy which weighs 1 kg and it has been duplicated at different, which we use as a standard. Well, it is accepted, this is 1 kg. So also when I say length is in meters, what is a meter? Again a reference kept at the same lab since maybe last 150 years or so, and this is a particular length scale which is given. The length of this standard is 1 meter, it is again an exotic alloy of platinum rhodium. But then there are some problems. Over the last 150 years, it is stored in the best condition. You have some duplicates in other countries also. It keeps eroding. Whatever be this, some changes take place. Therefore, it is not a good standard. We need a better standard. How will you have a better standard? Therefore, what happened was in the year 1982, quite recently, people said, when I have a length standard, when I say a meter, I go and say, well, a meter is so long and is the length of a standard. Instead of doing this, can I express the length standard through physical constants? What is the constant I must use, which so that whatever happens, the length is the same, it cannot change. Maybe after a million years the meter will still be the same. The physical constant used for defining the length is velocity of light in vacuum. All of us know that light is propagated as an electromagnetic wave, and the speed at which light is propagated we say is c meters per second. The question is, can we use this constant, it is a constant because the electromagnetic waves propagate through vacuum at a constant speed, let us say c meters per second, and rather than define the length in terms of a standard like what we considered a standard of so much length which is kept near Paris, we would like to define it with respect to this physical constant. And how do we do that? Well, if I could have, let us say, a length, we are interested in the length to be defined as 1 meter, we say the distance travelled by light in 1 over c seconds is what constitutes 1 meter. How do we look at it? The speed of light is c meters per second. The light travels at a speed of c meters per second. The duration we are considering is 1 over c, so much seconds, second and second gets cancelled and we get 1 meter. Therefore, the more recent definition of length scale is with reference to the velocity of light in vacuum, which is c. The precise value of c is, we told ourselves earlier, the speed is around 3 into 10 to the power 8 meters per second, 299, 792, 458 meters per second. Therefore, the definition of length of 1 meter is the distance travelled by light in vacuum over a duration of 1 over 299, 792 and 458 seconds. This is how we define the length scale as a meter. Therefore, what is it we have done so far? We have considered something like the definition of mass as a standard kilogram, maybe length as a standard meter, but now we are telling ourselves meter corresponds to the distance travelled by light in vacuum for a duration of 1 over, let us say, 299, 792, 458 seconds. But then we have still not defined time. And how do we define time? We must be very clear. Time is something related to the duration. Let us say you have a pendulum, the pendulum goes up and down, the duration of one cycle of the pendulum, maybe pendulum starts here, goes here, comes back here, is what we say is a duration of this pendulum, which we say as 1 second. But then it is difficult to have a period like a pendulum being used to describe the time scale, and it's easier for us to define the time scale based on the duration of an event. And which is the event which is most simplest to describe? We have the earth maybe revolving around its axis, and it looks at the sun. One revolution of the earth around its axis is what we call 1 day. Maybe we call midday, middle of the day, as when the sun is vertically above us. Maybe the sun is vertically above a particular part of the earth, we call it as midday, and we go to the next midday, next time the sun is vertically above, and that corresponds to one period of rotation, and we call it as 1 solar day. That means in 1 solar day, a day consists of 24 hours, again each hour consists of 60 minutes, each minute consists of 60 seconds, and therefore the 1 solar day consists of something like let us say 86,400 seconds. Now, but there is one problem in this. See, earlier we told the earth is rotating around the sun, and as it is rotating on its axis and revolving around the sun, the period of rotation is not exactly 1 day, but it is slightly shorter, because it is also, as it is rotating on its axis, it is also revolving, and therefore the exact period of one rotation around the sun is not 1 solar day, but it is something like, instead of being 24 hours, it is 23 hours 56 minutes and something like 45 seconds, and this duration is what is known as a sidereal day. Therefore, we have complicated the issue. Instead of having one solar day, we said, well, we need something like a sidereal day which is slightly smaller than 86,400 seconds, but still further, you know, there are perturbations in the rotation and also in the path around it, and therefore it is very difficult to really define time very accurately in terms of either sidereal day or in terms of solar day, and it is really necessary to have some other standard for defining time. Therefore, the scale or the standard for defining time is defined through some other standard for defining time, that is seconds. And how do we do it? Maybe you know cesium, and this cesium, we have cesium 133, it is an isotope element and it emits radiation. It emits radiation in different bands. And what do we mean when something emits radiation? You know, maybe it is emitting packets in some wavelets and it keeps on emitting at some frequencies, and each of them is a period, so many periods of radiation is getting emitted. Therefore, we look at one specific band, namely at the ground state of cesium, and at this ground state of cesium you take maybe one hyperfine level and you say so many number of periods which are emitted, that means you say specific number of periods of radiation which is emitted at the ground state in this particular hyperfine level is what we will call as 1 second. Therefore, how do I put this hyperfine level? Let us again tell this. Well, at this ground state cesium is emitting radiation. Each wavelength, from here I go here, each wavelength corresponds to a specific period. I count a large number of these wavelengths, and the number of periods or number of wavelengths amounting to something like 9, 192, 631, 770 periods or wavelengths corresponding to this ground state at the hyperfine level is what is 1 second. What do I mean by this? Just to make sure we are very clear, you have one period of radiation or one wavelength. This wavelength corresponds to a time of 1 over 9, 192, 631, 770 seconds, and this is how we define time. Namely, in this ground state of cesium, the 9, 192, 631, 770 periods of radiation emitted is what constitutes 1 second, and this is an accurate way of defining time. Therefore, what is it we have done so far? Let us quickly recapitulate. We have defined mass as a standard, we have defined length as a standard. Length as a standard, we said we will define on the basis of the velocity of light. Then we said yes, we need to define seconds as a, or time as a standard, and therefore we now know, yes, I have defined mass, length, time, mass, length, time, and now we can derive a set of units. The length or distance divided by time has units of meter per second, and this is what we call as velocity. When I say distance, distance could be a vector and therefore velocity is a vector, and if I say momentum, we say mass into velocity, or rather the units is equal to kilogram into meter per second. This becomes momentum. We say change of momentum is impulse, and therefore impulse will have units of same as momentum, namely kilogram meter per second. We went forward and said that rate of change of momentum is what constitutes force, or rather the impulse divided by time is force, and therefore force could be defined as rate of change of momentum, that is 1 over second, into we have momentum as kilogram meter per second, or rather the units of force becomes kilogram meter per second square, which is what we call as Newton. Therefore, we have defined through these three basic definition of mass, length and time: velocity meter per second, momentum kilogram meter per second, impulse again kilogram meter per second, and force which is kilogram meter per second squared. Having defined these quantities, maybe it is time to go forward and examine how we can describe using these units the motion in space of the different bodies, and this is what we will do in the next class. Thank you then.